Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. Matter seems solid because our senses stop probing too soon. Physics, however, never hesitates. When experiments strip matter down to what is directly measurable, solidity quietly vanishes. Light carries energy but no intrinsic mass. Electrons act as point-like entities, offering no interior to examine. Protons persist without being truly elementary. Gravity responds to energy itself, not to any tangible stuff. These are not analogies, they are precise outcomes, verified through careful experimentation. Tonight, you will trace the questions that physics had no choice but to confront. Each arose as matter was stripped to its essentials: how light can contribute to mass without creating new particles, why mass exists at all, why nature prefers two dominant mass scales, the electron and the proton, rather than a continuous spectrum, why these states carry charge, and why charge never escapes the influence of gravity. You will see how electrons and protons transform into neutrons, how neutrons bind and unleash vast energy, and how all of this occurs even when particles show no internal structure. You begin where ordinary explanations fall silent. Part 1. How light, or its mathematical equivalent, can act like a stable mass-bearing state. Photons have no rest mass. This is not a philosophical claim but one of the most rigorously tested facts in physics. From early electromagnetic experiments to modern high-energy collisions, every measurement confirms it. A free photon has no rest frame and carries no intrinsic mass. Yet light clearly possesses energy. It carries momentum, exerts pressure, curves spacetime, and participates in gravitational interactions. This introduces a subtle tension. If mass is a measure of energy that cannot be removed, can light ever behave in a way that resembles mass? This is not speculation. It arises from the definition of mass in relativity. Mass is not a substance but a manifestation of energy confined in a persistent arrangement. Whenever energy is trapped or constrained in a lasting configuration, it contributes to inertia and gravitation. So the question is not whether light can influence mass, it can, but whether it can form a stable, particle-like state rather than just a transient effect. A natural starting point is the concept of a confined photon. Picture a perfectly reflective cavity, or a finely tuned electromagnetic resonator. Photons inside do not escape. They bounce, interfere, and form standing wave patterns. Energy builds within the cavity, and by relativity, this energy increases the system's total mass proportionally to E/c2E/c2E/c2. Importantly, this mass belongs to the system as a whole, not to individual photons. A cavity filled with light becomes slightly heavier than an empty one. This is measurable in principle, though delicate in practice. Tiny energy differences are dwarfed by everyday masses, and isolating environmental noise is difficult. Yet related phenomena, radiation pressure, shifts in resonant frequencies, and the inertia of electromagnetic systems, confirm the effect. Experiments with superconducting microwave cavities, optomechanical resonators, and ultra-stable oscillators routinely operate in this regime. The lesson is clear: light can contribute to mass at the level of a composite system. It explains why heated objects weigh a little more than cold ones and why stored field energy affects inertia and gravity. However, this mechanism has limits. No new particle appears. The photon remains massless, and the extra mass disappears once the energy is released. Confined light alone cannot account for stable elementary particles like electrons or protons. To go further, gravity must be included. In general relativity, energy bends spacetime, and curved spacetime guides energy. This feedback opens a bold possibility. Could electromagnetic energy warp spacetime enough to trap itself, forming a self-sustaining configuration with an effective rest mass? John Archibald Wheeler explored this idea in the mid-20th century, calling such objects geons, gravitational, electromagnetic entities. A geon is not a conventional particle but a localized knot of electromagnetic radiation, held together by its own gravitational field. Here, the field shapes the geometry, and the geometry confines the field. Mass emerges, not from matter, but from the interplay of energy and spacetime. Geons have what could be called an effective rest energy, the minimum energy necessary to sustain their structure, and from this arises an effective mass. No extra ingredients are needed. These solutions simply emerge from the mathematics of Einstein's equations coupled to electromagnetism. Yet nature is not generous to them. The energy densities required to form a geon are enormous, and most such configurations are unstable, slowly leaking energy or unraveling under minor perturbations. Over time, they dissipate. This fragility is not coincidental. It follows directly from the behavior of electromagnetic fields under gravity. If geons existed in abundance, they would appear as objects that influence gravity and electromagnetism but remain invisible in chemistry, nuclear physics, and the familiar interactions of matter. Extensive astronomical surveys, from gravitational lensing studies to precise measurements of the cosmic microwave background, have revealed no signs of such entities. So here you pause at the edge of the first inquiry. Light can increase the weight of a system. Energy can warp spacetime. Fields and geometry can temporarily support each other. Yet stable matter does not emerge so easily. Allow that insight to settle. Physics follows what persists. The universe is structured, restrained, and quietly consistent, guiding your thoughts to slow down and drift along with it. Although geons are conceptually intriguing, they do not explain the persistent matter around you. Neither confined light nor gravitationally bound radiation produces particles that endure for billions of years. Their inability to do so opens a deeper question. Perhaps particles are not tiny objects at all, but stable patterns, long-lasting arrangements in more fundamental fields. This leads to a more ambitious idea: stable field configurations, often called solitons. In certain nonlinear field theories, energy can form localized, self-sustaining patterns that do not disperse. These structures do not need external walls or gravity to stay intact. Their stability is built into the equations themselves. The fields naturally settle into shapes that cannot smoothly relax into emptiness. Some intrinsic property prevents them from unwinding. Often, this protection is topological. The configuration carries a kind of mathematical identity, an invariant that cannot be erased without crossing a large energy barrier. As long as that barrier exists, the structure persists. The energy required to maintain it becomes fixed and unavoidable, behaving exactly like rest mass. It is independent of motion. It simply exists. Such structures can resemble particles in many ways. They can have finite size, carry discrete charges, and support distinct excitation modes, much like musical notes on a string, but here the rhythm is mathematical rather than audible. Through this lens, electrons and protons need not be imagined as point-like objects with built-in properties. Instead, they can be seen as stable knots in deeper fields. Light remains a free, linear wave, while massive particles emerge where nonlinear interactions lock energy into place. This distinction is crucial. Linear waves spread and overlap without restriction. Nonlinear structures can confine energy, forming quiet, persistent patterns. For a particle to emerge from energy, the theory must permit such nonlinear locking or topological protection. Standard quantum electrodynamics, with its linear equations, does not allow stable solitons. Beyond these familiar equations, however, nonlinear solutions appear naturally. In non-abelian gauge theories, in models with broken symmetries, and in speculative approaches to quantum gravity. Even the proton offers a hint. Most of its mass comes not from the bare mass of its quarks but from the energy of the strong interaction fields binding them. Experiments in the late 20th century confirmed this. Here, mass emerges dynamically from the energy stored in fields. If particles are indeed solitonic structures, subtle signs should exist. Tiny deviations from perfect point-like behavior or excited states corresponding to slight deformations of the field configuration. High-energy experiments, such as those at CERN, have searched for such features. Electrons appear point-like down to extraordinarily small scales. Protons reveal internal structure consistent with quantum chromodynamics. These results push the soliton hypothesis beyond current experimental reach, suggesting that any deeper fields would operate at energy scales where known forces merge into something more unified. Stepping back, a clear pattern emerges. Light can add mass collectively. Electromagnetic energy can curve spacetime. But stable, long-lived particles most plausibly arise from nonlinear field structures protected by deeper symmetries and conservation laws. There is no straightforward way to turn a photon into an electron or proton using well-tested physics. This absence is not a failure, it is a guide. Equations tested to extraordinary precision refuse to allow such transformations. The resistance of light to becoming matter reveals something exact about the architecture of physical law. As one physicist reflected, understanding deepens through boundaries. Photons do not transform into massive particles. That constraint points to the next question. If mass cannot arise from light alone, what mechanism governs the stable masses we observe? Why do only certain mass scales exist? These questions carry you forward, toward a new perspective. Mass is not substance, but energy that cannot escape, energy bound by enduring patterns in fundamental fields. As this thought settles, let your mind slow. Physics moves patiently, guided by what persists. You can pause here, knowing that every unanswered question is not a gap, but an invitation to explore the quiet, structured depths of reality. When a configuration holds together, its energy remains present. In general relativity, that alone suffices. Energy does not need to be tangible to matter, it only needs to persist. Spacetime responds, inertia shifts, gravitational influence arises. Mass appears naturally, measured as stored energy divided by the speed of light squared. This is not abstract. It manifests in everyday systems. A charged capacitor weighs slightly more than an uncharged one. A superconducting loop carrying a persistent current contributes subtly more to gravity. These effects are small but real, consistent, and unavoidable. Space agencies account for them when modeling sensitive spacecraft, resonators, and ultra-stable instruments. Mass, in this sense, is energy that has lost its freedom to escape. Yet the boundary is clear. This mass is a property of the system holding the energy, not the photon itself. No new particle emerges. The moment the energy is released, the extra mass vanishes. Light can add weight, but it cannot generate electrons or protons. To create lasting mass, energy must be confined by its own influence, not by external walls. This leads you to an even deeper possibility. In Einstein's universe, energy does more than move through space and time. It shapes it. Electromagnetic fields carry energy and momentum, and that energy bends geometry. Curved geometry, in turn, guides the paths that energy takes. When these effects feed back into each other, a striking question emerges. Could energy hold itself together, without mirrors, walls, or containers, forming a lasting, self-sustaining structure? The reasoning unfolds step by step. Fields carry energy. Energy curves spacetime. Curved spacetime redirects fields. If that redirection perfectly counteracts the natural tendency to disperse, a localized configuration can persist. Such a structure would have a minimum energy that cannot be removed without destroying it, a quantity behaving exactly like rest energy. Dividing it by the square of the speed of light gives an effective mass. John Archibald Wheeler explored this idea and coined the term geon. A geon is not a particle in the conventional sense. It contains no material core, it is a knot of energy, held together by the geometry of spacetime itself. Here, matter dissolves into structure. Fields and geometry do all the work. Nothing else is needed. The elegance is undeniable. Mass emerges purely from energy and curvature. Yet nature is exacting. The energy densities required are enormous, and even minor disturbances destabilize the configuration. Most geons slowly leak energy and fade. Their lifetimes hinge delicately on symmetry and idealized conditions. In realistic environments, they unravel. If such objects were common, their presence would be noticeable. They would bend light and gravity while remaining invisible to chemistry and nuclear processes. Astronomical surveys, gravitational lensing maps, cosmic microwave background studies, and precision cosmology leave little room for them. Geons are mathematically valid, but physically elusive. They show that mass can emerge from energy and geometry alone, but they cannot account for the stable matter we observe in the universe. The inquiry deepens further. The third path does not depend on external confinement or delicate gravitational balance. It treats mass as an intrinsic feature of stable field patterns themselves. This is the domain of solitons and topological structures. In many nonlinear field theories, localized configurations exist that refuse to disperse. Their persistence is not granted by outside forces but by the structure of the equations themselves. The field cannot unwind smoothly into emptiness. Energy barriers prevent it. Once formed, such a configuration cannot fade without crossing a steep barrier. The energy needed to maintain it is fixed, independent of motion, and behaves just like rest mass. Here, mass is not a label. It is the energy cost of existence itself. This idea already appears in known physics. Consider the proton. Its mass is not primarily set by the bare masses of its quarks. Instead, most of its mass arises from the energy stored in the strong interaction fields that bind them. Experiments at SLAC and CERN confirmed this with precision. What makes a proton heavy is mostly field energy locked into a stable configuration. Soliton-based interpretations extend this logic. Particles may be enduring patterns in deeper fields, stabilized by symmetry and topology. Properties like mass, charge, and interaction behavior emerge from how the configuration fits within allowed states. These structures are not arbitrary. They predict subtle signatures, finite size, characteristic excitations, slight deviations from point-like behavior at extreme energies. This is why accelerators probe ever smaller scales. Electrons appear point-like down to astonishing distances. Composite particles reveal structure exactly where expected. The absence of solitonic signatures at accessible energies does not rule them out. It simply places them beyond current reach, into deeper layers of physics yet to be explored. Among the three mechanisms considered so far, this one stands apart. It alone can produce stable particles with discrete masses and intrinsic properties, without relying on external confinement or fragile gravitational balance. Mass arises not as an addition, but as a necessity. The distinction is critical. One mechanism creates mass that is collective and temporary. Another produces mass that is conditional and fragile. This one produces mass that endures. None of these ideas contradict observation. Yet their coexistence is strictly bounded. Symmetry, conservation laws, and measurement draw firm lines. As one physicist once reflected, science is less a collection of facts than a disciplined way of thinking. And here, that discipline is everything. If mass were easy to create, the universe would overflow with stable structures of every energy imaginable. Chemistry would collapse, and order would dissolve. Instead, matter is sparse, selective, and structured. Stability is rare. And that rarity points forward. If mass arises only when energy is trapped in highly specific, non-escapable forms, another question naturally follows. Why does nature favor only a few dominant mass scales instead of a continuous spectrum? Let that thought settle. Physics asks only what must be asked. For now, it is enough to rest in the calm realization that stability, like sleep, only appears when everything unnecessary has quietly fallen away. Stability is never a gift. It is something nature enforces through constraint. A physical configuration endures not simply because the equations permit it. Permission does not equal persistence. For a system to last, there must be no pathway, smooth or abrupt, by which it can shed its energy while still obeying conservation laws. If such a pathway exists, the system follows it immediately, without resistance, hesitation, or mercy. For a configuration to remain, three silent conditions must all hold at once. First, it must be unable to radiate energy freely. Anything that can leak energy through waves, particles, or field disturbances will do so until it dissolves or transforms. Second, any enduring configuration must respect the fundamental symmetries of nature. These symmetries are not mere abstractions, they are the guardians of conservation laws. Break one, and protection against decay disappears. Third, the system must have no lower energy state that shares its conserved properties. If such a state exists, energy will inevitably flow downward. Nature always seeks release. Almost every imagined structure fails immediately. Some violate symmetry before they even form. Others have obvious ways to radiate away their energy. Many endure only briefly, vanishing the moment a slight disturbance appears. Stability, then, is rare. It is exceptional. This alone rules out a smooth, continuous spectrum of stable masses. A continuum would mean structures arbitrarily close in energy, connected by gentle pathways. Gentle pathways allow decay. True stability requires isolation. And this is exactly what isolation provides. In theories with solitons or topological structures, the landscape of possible field configurations is not uniform. It is divided, sliced into separate regions by symmetry and topology. These divisions arise naturally from the mathematics of the fields, they are not imposed by choice. Gauge symmetries, global symmetries, and topological constraints carve configuration space into distinct sectors. Within each sector, the system seeks the lowest possible energy. That lowest state is stable, not because it is favored, but because there is nowhere else it is allowed to go. These stable states appear as isolated valleys in a vast terrain. They are discrete. Their energies, and therefore their masses, are set by the structure of the theory. Seen in this light, the electron and proton are not accidents. They correspond to deep, isolated minima. They are not part of a smooth continuum. Between them lie higher energy regions that cannot support rest. Anything placed there inevitably slides downward until it reaches one of the few stable valleys. This explains why intermediate masses do not persist. A deeper question emerges: why aren't there infinitely many such valleys? In principle, a complex theory could allow countless stable configurations. But physics constrains relentlessly. Imagine a universe filled with infinite stable particles. Energy would splinter endlessly. Matter would fracture. Chemistry could not settle. Stars would lose control of fusion. The cosmos itself would collapse into chaos. This is not our universe. Experiments confirm the opposite. High-energy collisions briefly create a menagerie of possibilities. Almost all decay almost instantly. Resonances flicker and vanish. Exotic states appear only under extreme conditions, dissolving as soon as those conditions fade. This teaches a profound lesson. Configuration space is filtered with extraordinary rigor. Only structures that satisfy every constraint survive. Stability is not merely rare, it is fiercely restricted. Within this filtered world, the electron and proton occupy a unique place. Not because they are simple, but because they are terminal. In the language of dynamics, they are fixed points. A fixed point is not frozen. It is a state from which no energetically allowed path leads downward while preserving the required symmetries. The electron is one such point. Its conserved quantum numbers forbid decay into anything lighter. No lower energy state with the same identity exists. It cannot split without violating the rules. Once formed, it persists. The proton is different, yet equally bound. Its internal structure, held together by the strong interaction, cannot decay without either increasing energy or breaking conservation laws. An isolated proton has no accessible escape route. This is no coincidence. Both particles sit at the bottom of their stability basins. Beneath them, there is no slope. Everything else slides. This overturns comforting intuition. One might imagine electrons and protons exist because nature chose them. The truth is harsher. Everything else is discarded. Configurations that can lose energy do so. Those that violate symmetry never survive. Those with lower energy alternatives vanish. After relentless elimination, only a few remain. They are not favored, they are unavoidable. This process never stops. In the early universe, extreme energies filled configuration space with possibilities. As the cosmos cooled, unstable forms disappeared. In modern accelerators, the same story plays out on smaller stages. Many states appear. Almost all fade. What endures are those that cannot escape. This explains why electron and proton masses are sharply defined. Stability depends on multiple conditions acting together. Each constraint removes vast regions of possibility. Only where all constraints intersect does mass persist. Where they do not, nothing lasts. These masses are not arbitrary numbers awaiting fine-tuning. They mark the rare places where stability is even possible. Earlier, you saw that bending light alone cannot create lasting matter. You saw that mass arises only when energy is trapped in unavoidable forms. Now you see why such forms are scarce. Nature cannot allow infinite stable masses without destroying order. Stability is restrictive, not generous. And once only a few stable configurations exist, everything else, charge, interactions, binding, arises naturally from how those configurations coexist with the fields and with one another. That necessity quietly leads to the next question. Why do these survivors carry electric charge at all? A configuration that endures cannot remain a silent mathematical artifact. Once it persists, it must live among fields, remain identifiable under transformations, and obey the same symmetries governing every interaction. Electric charge emerges exactly here, not as decoration, not as an afterthought, but as a direct consequence of demanding consistency in a universe governed by gauge fields and symmetry. Persistence is their signature, and persistence is never free. For a configuration to continue existing, it must satisfy conditions that leave almost no room for choice. It must remain dynamically steady. It cannot leak energy into lower states. It must remain recognizable under every change of perspective. And it must interact with its surroundings without violating nature's quiet accounting rules. These are not philosophical preferences. They are enforced by decades of observation. From atomic measurements to quantum electrodynamics to the deepest scattering experiments ever performed. Within this tightly constrained world, electric charge does not appear as an extra feature. It is a necessity. A stable configuration cannot ignore its surroundings. Fields are not optional decorations, they are the medium of all interactions. Electromagnetic fields, in particular, fill every corner of space, from the smallest atomic distances to the void between stars. Anything that exists in this environment must respond consistently and predictably. That response cannot be arbitrary. If a configuration behaved differently depending on coordinates or descriptions, the very idea of physical law would collapse. Inconsistency would immediately undermine stability, opening paths to decay. Electric charge is the rule that prevents this. It defines how a configuration responds when the electromagnetic field is locally adjusted. It ensures that reality remains consistent, even as mathematical descriptions shift. In precise terms, charge tells us how a configuration transforms under local gauge symmetry. Without this specification, interactions would be ambiguous. And ambiguity is incompatible with persistence. Charge is not something added later. It is woven into the conditions that allow the configuration to form in the first place. Imagine a configuration with no charge at all. It would not respond to electromagnetic fields. It could neither emit nor absorb photons. It would leave no signal in detectors, no signature in almost any instrument ever built. More deeply, it would lack a stable identity. Without interaction, there is no operational way to distinguish it from empty space. In physics, this is not a philosophical concern. It is a practical one. If nothing can reveal the presence of a configuration, then no experiment can confirm that it exists as something separate from the vacuum. Electric charge marks the threshold at which existence becomes measurable. This does not mean every stable structure must be electrically charged in an obvious way. Neutral systems exist, but their neutrality arises from internal balance, not from the absence of interaction. At the most fundamental level, the components that form neutral structures still obey charge-related transformation rules. Neutrality is a cancellation, not a disappearance. The discrete nature of charge follows from the same logic. Stability requires isolation from nearby lower energy alternatives. If charge varied continuously, configurations could drift gradually between interaction behaviors, always finding a slightly more favorable state. Such smooth drifting would erase stability entirely. Instead, symmetry divides configuration space into separate regions. Each region corresponds to a specific transformation rule under electromagnetic symmetry. A configuration belongs wholly to one region or another. Moving between them is not gentle. It requires violating charge conservation, and no such violations have ever been observed. This structure explains why electrons and protons carry charges of equal strength and opposite sign. They occupy distinct symmetry sectors that cannot be smoothly connected. Their charges are not numerical accidents. They are identifiers, marking which sector each configuration inhabits. This picture is grounded in experiment. From early measurements to modern collider data, charge quantization has been confirmed with extraordinary precision. No deviation has ever appeared, even at the highest energies explored. The necessity of charge becomes even clearer when you consider interaction itself. A stable configuration must not only resist decay, it must resist deformation. Electromagnetic fields fluctuate constantly. A configuration that responds inconsistently to those fluctuations would experience forces that tear it apart. Charge determines how those forces act. It defines direction and strength in a way that preserves internal coherence. Without charge, or with ill-defined charge, electromagnetic fluctuations would act unpredictably, introducing instability rather than interaction. This is why charge is best understood not as a substance, but as a rule of engagement. It does not describe what a configuration is made of. It describes how it participates in the shared structure of physical law. The electron illustrates this perfectly. Experiments have revealed no internal structure down to the smallest scales probed. Its stability is absolute within current limits. That stability depends on the strict conservation of its charge. No process has ever been observed that allows an isolated electron to alter its charge without breaking fundamental symmetries. This conservation is not imposed arbitrarily. It arises from the transformation rules required for consistent interaction. If an electron could change its charge continuously, its interaction with the electromagnetic field would lose coherence. New decay paths would open. None are observed. The proton tells a different story, yet arrives at the same conclusion. It is not elementary, but it is stable across cosmic time. Its charge reflects the net transformation behavior of its internal configuration. Though its constituents carry fractional charges, the proton as a whole occupies a single, well-defined symmetry sector. That assignment allows it to bind with electrons, form atoms, and build chemistry. In both cases, charge is not the cause of stability. It is the condition that makes stability possible. From this, another consequence follows naturally. Charge cannot simply be removed. A hypothetical configuration identical to an electron in every respect except charge would not behave like one. It would not bind to protons. It would not participate in atomic structure. And without electromagnetic interaction, it would struggle to remain localized in a world filled with fluctuating fields. Its absence from observation is not surprising. It is expected. Stable configurations that participate in matter must carry charge. Neutrality is permitted only when internal charges balance, preserving interaction at deeper levels. Charge can cancel, but the rules governing charge never vanish. A neutral atom still responds through polarization and subtle effects. Complete isolation never occurs. This persistent interaction keeps configurations embedded in the web of physical law and prevents the emergence of disconnected, unobservable entities. Over time, this understanding emerged slowly. Early models imagined charge as a fluid or substance. Later developments, especially in gauge theory, revealed it as a manifestation of symmetry itself. Work throughout the 20th century showed that charge conservation is inseparable from the structure of electromagnetic interaction. Modern experiments continue to confirm this view. By now, a clear pattern has formed. Mass is the energetic cost of persistence. Charge is the rule that allows persistence to remain consistent under interaction. Neither arises from hidden material components. Both arise from constraint. Energy and charge together place every stable configuration into the broader structure of interaction. And energy, in any form, carries one final consequence. Unlike charge, it cannot be screened or cancelled. Every configuration that exists must influence and respond to the geometry of space and time itself. This is not a shift in topic. It is the next step forced by the same logic. Stability, interaction, and symmetry do not stop with electromagnetism. They extend into spacetime. And that extension leads you quietly to the next question. Why must these configurations interact gravitationally? Gravity's most unsettling feature is not its weakness, but its inevitability. You can shield charge. You can neutralize it. You can arrange matter so electromagnetic forces nearly vanish. But no experiment, from laboratory scales to deep space observation, has ever found a way to hide from gravity. The reason is simple. Once a configuration persists, it carries energy. And energy does not merely reside within space. It reshapes space and time themselves. That reshaping is what you experience as gravity. Mass emerged as the cost of persistence. Charge emerged as the rule of consistent interaction. Gravity now enters as the unavoidable consequence of energy's presence. It is not philosophical. It is written directly into equations that have survived every test so far. And as you rest with this thought, gravity waits ahead, not as an added force, but as the final expression of existence itself. At first glance, gravity seems to resemble the other forces you already know. Objects attract one another. Influence travels across space. Something reaches out and pulls. But this resemblance fades the moment you look more closely. Electric forces depend on charge. Strong forces depend on color charge. Weak interactions depend on particle identity. Gravity depends on none of these. It responds only to energy and momentum, no matter how that energy is arranged. An electron and a proton push and pull electromagnetically in opposite ways because their charges differ, yet gravitationally they behave almost the same once their total energies are counted. A neutral atom, with no external electric field at all, still weighs something. Even light itself, photons with no rest mass, follows curved paths near massive objects. The reason is quiet and uncompromising. Gravity does not recognize charge. It recognizes energy. If energy is present and cannot be removed, gravity cannot be avoided. This became clear when gravity was no longer treated as a force, but as geometry. In Einstein's view, energy and momentum tell spacetime how to curve, and that curvature tells everything else how to move. The equations make no distinction between energy stored in mass, pressure, radiation, or fields. All of it counts. All of it bends the same fabric. This universality has been tested again and again. Light bends around stars. Binary pulsars lose energy exactly as predicted when field energy contributes to gravity. Objects of different composition fall the same way in Earth's field with astonishing precision. There is no hidden exemption, no special case. Gravity couples to everything that carries energy. And a stable configuration, by definition, cannot discard its energy without ceasing to exist. So the interaction is unavoidable. At first, electric charge might seem like a loophole. Charges can cancel. A positive and negative charge together leave no external electric field. But cancellation belongs to electromagnetism, not to energy itself. Even when fields cancel outwardly, The energy that made that cancellation possible remains stored in the configuration. That energy still shapes spacetime. There is no such thing as non-gravitating charge. Every charged configuration carries electromagnetic field energy. That energy enters the gravitational equations on equal footing with all others. The equations do not permit exceptions. This leads to a crucial shift in perspective. Gravity is not an extra force layered onto nature. It is the response of spacetime itself to the fact that something exists. If a stable configuration is present, spacetime cannot remain flat unless the total energy is exactly zero. And exact zero energy configurations do not persist. Existence bends geometry. This also dissolves a common confusion. Why does gravity seem so weak compared to electromagnetism? Because they measure different things. Electromagnetism compares charges. Gravity compares energy densities. At everyday distances, charge interactions dominate. But weakness does not mean optional. Gravity acts everywhere, always, without exception. The bending of starlight observed during the early 20th century made this unmistakable. Photons feel no force in the traditional sense. Yet their paths curve because the space they travel through is curved. Gravity influences motion not by pushing, but by shaping the stage itself. Another quiet fact emerges here. Gravity always attracts. It never repels. This is not a coincidence. Electric charge comes in opposite signs that can cancel. Energy does not behave this way for stable configurations. While certain theories allow fleeting negative energy densities, lasting structures in nature retain positive total energy. That positivity gives spacetime curvature a single sign. Paths converge rather than diverge. Attraction dominates. This is why gravity builds galaxies, clusters, and the vast cosmic web. Not by choice, but by necessity. The impossibility of gravitational shielding follows naturally. You can block electric fields. You can redirect magnetic ones. But you cannot block gravity, because blocking gravity would require removing energy itself. And removing all energy would erase the configuration entirely. Even the most carefully balanced neutral systems still possess rest energy. That energy curves spacetime. The curvature remains. Every precise experiment designed to challenge this conclusion has confirmed it instead. Gravitational and inertial mass are indistinguishable. All forms of energy fall the same way. Pressure, radiation, binding energy, none are exempt. Seen together, these are not scattered facts. They are expressions of a single demand. Stability requires energy. Energy demands geometry. As physics matured, this understanding deepened. Gravity was once imagined as an invisible pull across space. That idea struggled to include field energy and radiation. Geometry resolved the conflict. Later discoveries showed that pressure and stress gravitate too. Modern cosmology depends on this. Stars balance radiation pressure against gravity. Black holes form from energy alone. Gravitational waves carry energy by rippling spacetime itself. Nothing about this requires hidden material substance. The interaction is purely geometric. From the path you have followed, gravity completes the picture of existence. Mass measures the energy required to persist. Charge governs how persistence remains consistent under electromagnetic interaction. Gravity describes how that energy reshapes the space and time in which everything unfolds. These are not separate traits. They are consequences of the same requirement: consistency under interaction and endurance under change. Gravity is universal because existence is universal. Charged particles gravitate not because of their charge, but because charge cannot exist without energy, and energy cannot exist without geometry responding. Even neutral atoms gravitate. Their mass includes binding energy, motion, and field energy. Even seas of radiation gravitate. In the early universe, light itself shaped expansion and structure. Gravity responds to what exists, not to how existence is labeled. And once you see gravity this way, the next step becomes unavoidable. If stable configurations can exist, interact, and reshape spacetime, then sometimes they must also transform. But transformation cannot be free. When stable configurations change form, the same constraints must still be obeyed. Energy must balance. Symmetry must hold. Conservation laws must remain intact. That brings you gently to the next question. How can an electron and a proton ever become something else at all? If they could merge simply because they attract, matter would dissolve everywhere. Hydrogen would collapse into neutrons. Chemistry would never form. Stars would never shine. The fact that this does not happen tells you something profound. The conversion of an electron and a proton into a neutron reveals the exact boundary between what interactions are allowed to do and what they are fundamentally forbidden from doing. Electrons, protons, and neutrons are not mechanical objects assembled from parts. They are stable configurations defined by energy, symmetry, and conservation. Transforming one into another means replacing one allowed configuration with a different one, without breaking any of the rules that made stability possible. This immediately excludes almost all familiar forces. Electromagnetism can move charges, bind atoms, and shape chemistry. But it cannot rewrite identity. An electron remains an electron. A proton remains a proton. The equations forbid anything else. Gravity is even more limited. It responds only to energy and momentum. It cannot see the internal labels that distinguish particles. It bends paths, not identities. If electron-proton conversion relied on either of these interactions, it would never occur. Only one interaction has the authority to do this: the weak interaction. Not because it is strong, but because it is different. It alone allows particle identity to change while preserving the deepest conservation laws. In a process called electron capture, an electron is absorbed by a proton. Inside the proton, one up quark quietly transforms into a down quark. The configuration rearranges itself. The proton becomes a neutron. This transformation is not arbitrary. It is mediated by the weak interaction's charged current, carried by a W boson. No electromagnetic pull or gravitational compression can replace this role. And something else must happen. A neutrino must be released. Without it, conservation would fail. Energy, momentum, angular momentum, spin, and lepton number would have nowhere to go. The neutrino carries away exactly what cannot remain behind, slipping through the universe almost without interaction. Here again, nothing is optional. Every detail is enforced by constraint. And as you rest with this realization, the universe feels less like a collection of objects and more like a quiet negotiation between what is allowed and what is forbidden, a balance that permits stars to shine, matter to endure, and the night sky to remain gently, reassuringly ordered. This is why the neutrino was predicted long before it was observed. It was not invented to patch an anomaly, it was demanded by the conservation laws themselves. When neutrinos were finally detected, they confirmed that the weak interaction obeys those laws with extraordinary precision. In electron capture, the neutrino is not a byproduct. It is the accounting mechanism that makes the transformation possible. Another constraint must be emphasized: the process does not occur freely. A neutron is slightly more massive than a proton. Creating a neutron from a proton and an electron requires additional energy. In free space, no source provides that energy. As a result, isolated electrons and protons do not spontaneously convert into neutrons. Electron capture becomes possible only in specific environments where the total energy of the system decreases after the conversion. Inside certain atomic nuclei, replacing a proton with a neutron can lower the overall nuclear energy due to changes in nuclear binding. The energy difference is released via the neutrino. This selectivity is not a complication, it is evidence that the rules are being enforced consistently. The environment plays a crucial role. Stability is not an absolute property of a configuration in isolation. It is defined relative to the energy landscape surrounding it. Electrons and protons remain stable as separate entities in most circumstances. Only inside certain nuclei does the combined configuration of a neutron become energetically preferred. The weak interaction provides the mechanism, the nuclear environment provides the energy incentive, and conservation laws regulate the transition. Remove any of these, and the process does not occur. There is no loophole. Historically, electron capture was first inferred from nuclear decay patterns unexplained by beta decay alone. Experiments revealed nuclei changing charge without emitting electrons. Later, measurements confirmed neutrino emission and verified the weak interaction mechanism. Astrophysical observations extend this understanding. In massive stars, electron capture is critical during core collapse. As electrons are absorbed by protons, electron pressure drops, gravity dominates, and the core collapses, triggering supernova explosions. The elements forged in these explosions seed future generations of stars and planets. This is not a marginal effect. It shapes cosmic evolution. From the perspective of stable configurations, electron capture demonstrates a deeper principle. Transformations are allowed only when they increase overall stability. The weak interaction does not randomly convert particles. It opens specific channels available only under precise conditions. This explains why the universe does not dissolve into neutrons, why hydrogen remains stable, and why stars burn steadily. These constraints are enforced universally. Importantly, electron capture does not require speculative internal structures beyond established quark content. It does not require hidden forces or violations of known symmetries. Everything involved, the weak interaction, quark flavor change, neutrino emission, and energy thresholds, has been measured, tested, and confirmed across multiple domains. This economy of explanation reflects how tightly nature restricts allowed transformations. At this stage, the logic has narrowed. Electromagnetism cannot change particle identity. Gravity cannot change particle identity. Only the weak interaction can. Electron capture is not one mechanism among many. It is the only one consistent with all constraints. Once neutrons exist alongside protons, a new problem arises. Neutrons carry no electric charge, while protons repel each other electrically. Yet atomic nuclei remain bound. The process that creates neutrons does not explain how they stay together with protons afterward. That binding is governed by a different mechanism operating at extremely short distances, the residual strong nuclear force. If neutrons and protons were subject only to the forces we encounter in everyday physics, nuclei would never exist. Electric repulsion would push protons apart. Gravity is far too weak to stabilize matter at microscopic scales. Yet inside every stable nucleus, neutrons and protons remain locked together with extraordinary persistence. The reason is not mysterious. It comes from a remnant of a much deeper interaction, so strong at its core that even its leftovers hold matter together. Protons and neutrons bind because of the residual strong nuclear force, a consequence of the strong interaction that confines quarks inside them. This force is not a new fundamental interaction or an added layer. It is the lingering effect of the same interaction that governs the particle's internal structure. Protons and neutrons are stable configurations of quarks held together by gluons. The strong interaction confines quarks so tightly that separating them requires enormous energy. While most of this interaction remains locked inside the nucleon, a small portion extends beyond the boundary. This extension is not a leakage of particles, it is a persistence of field effects, which manifests as the residual strong force. In a limited sense, it is analogous to how electrically neutral atoms attract via van der Waals forces. The whole atom is neutral, yet the internal structure leaves an interaction footprint. In nuclei, this effect is vastly stronger and critically important. This explains why neutrons can bind despite having no electric charge. Electric forces do not govern nuclear binding, they would actually oppose it. Proton-neutron binding is the most stable configuration in light nuclei, because the residual strong force depends on proximity, internal configuration, spin alignment, and spatial overlap of nucleon states, not on electric charge. When a neutron and a proton approach within about 1 femtometer, this force dominates, overwhelming electromagnetic repulsion. The short range of the residual strong force is essential. Beyond a few femtometers, it becomes negligible, ensuring that nuclear binding does not extend indefinitely. If it were long-range like gravity, matter would collapse into a single dense object. If too weak, nuclei would never form. Acting only when nucleons are nearly in contact, it produces finite nuclei with well-defined boundaries and predictable structures. This distance dependence has been confirmed through scattering experiments and nuclear spectroscopy. It is embedded in every successful nuclear model today, from shell models to effective field theories. The distinction between proton-proton and proton-neutron binding follows naturally from this picture. When two protons approach each other, the residual strong force attempts to bind them, while the electromagnetic force pushes them apart. Whether binding occurs depends on which effect dominates. In light nuclei, electromagnetic repulsion is significant, and a proton-proton pair alone does not form a stable bound state. A neutron changes everything. It contributes residual strong attraction without adding electric repulsion. The neutron acts as a stabilizing participant, allowing the nucleus to reach a lower energy configuration. This is why stable nuclei require neutrons. As the atomic number increases, more neutrons are needed to counterbalance the growing electric repulsion among protons. This balance is not aesthetic, it is enforced by energy minimization. At the deepest level, binding occurs because the combined neutron-proton configuration has lower total energy than the separated particles. This principle has appeared repeatedly throughout this series. A configuration forms only if it costs less energy to exist than the alternatives. Nuclear binding follows exactly this rule. When a neutron and a proton approach closely enough, the residual strong force reshapes their joint energy landscape. A potential well appears. If the well's depth exceeds the kinetic energy trying to pull the particles apart, a bound state forms. The resulting configuration is not merely two particles sitting side by side. It is a new state with its own energy minimum. Escaping that minimum requires energy input. Without it, the configuration persists. This is why nuclear binding releases energy when it forms and requires energy to undo. Historically, nuclear stability was deeply puzzling in the early 20th century. Electromagnetic theory could not explain it. Gravity was irrelevant. The discovery of the neutron in 1932 provided a critical clue, but the full picture only emerged after the development of quantum chromodynamics, the theory of the strong interaction. Realizing that nucleons are composite objects and that the strong force responsible for their internal stability could have residual effects resolved the puzzle. Modern nuclear physics relies on this framework. It is not speculative. It underpins calculations of nuclear binding energies, reaction rates, and decay pathways used in laboratories and astrophysical models alike. This mechanism also explains why nuclear binding is selective. Not all neutron-proton combinations form stable nuclei. Spin alignment, relative motion, and quantum statistics impose restrictions. These constraints arise naturally from the underlying fields and symmetries. They do not require additional assumptions. The result is a structured nuclear landscape. Some combinations are stable, others fleeting, and many impossible. This structure is not arbitrary. It reflects the precise balance of forces and constraints acting at the femtometer scale. Astrophysical evidence reinforces this view. In stellar cores, nuclear fusion proceeds only when conditions allow nucleons to overcome electromagnetic barriers and enter the range of the residual strong force. Once they do, binding becomes energetically favorable and energy is released. Stars shine because this mechanism works exactly as described. Supernovae occur when nuclear binding can no longer stabilize matter against gravitational collapse. Neutron stars form when nuclear and gravitational effects reach a new balance. None of these phenomena require new forces, they arise entirely from the residual effects of the strong interaction and the constraints it imposes. Mass reflects the energy required to sustain a stable state. Charge governs how that state participates in electromagnetic interactions. Gravity expresses how spacetime responds to the presence of energy. Residual strong binding determines whether neutrons and protons can remain locked together as a nucleus. Each layer builds on the previous ones without contradiction. No internal machinery is introduced. No extra assumptions are needed. Neutrons and protons bind not because they are pulled together by an added force, but because the universe allows and prefers configurations that minimize energy under the existing rules. One subtle point deserves emphasis. The residual strong force is not adjustable. Its strength and range are fixed by the underlying theory. The universe does not tune nuclear stability manually. Stability emerges automatically from the interaction structure. This is why nuclear physics is predictive rather than descriptive. Binding energies, decay modes, and reaction thresholds can be calculated and confirmed experimentally. Discrepancies are rare and informative. As this part comes together, the focus shifts forward. If neutron-proton binding produces stable nuclei and alters the energy balance of matter, attention turns to what follows from that change. When binding lowers the total energy of a configuration, the difference cannot remain hidden, it must be released. The form and scale of that release govern phenomena ranging from nuclear reactors to the lifetimes of stars. This shift from the mechanism of binding to the release of energy opens the next part. Why does the combination of a neutron and a proton release so much energy? The moment a neutron and a proton bind into a single nuclear configuration, an enormous amount of energy is released. Not because energy is created or a force suddenly turns on, but because the system abandons a costly way of existing and settles into a configuration that demands less energy to remain real. This release is compulsory, enforced by the accounting rules governing every stable structure in the universe. To understand why the released energy is so large, one must first let go of a deeply ingrained intuition. Binding is not an act of construction. In nuclear physics, binding is subtraction. What matters is not what is added, but what is no longer required. Before binding, the neutron and proton exist as two independent configurations, each with its own rest energy, internal field energy, and contribution to spacetime's stress energy budget. The total energy of the system is simply the sum of those two independent costs. There is no shared structure, no shared stability, and therefore no shared economy. After binding, the situation changes fundamentally. The neutron-proton pair becomes a single configuration governed by a joint stability condition. The system no longer needs to pay twice for existence. Some of the energetic cost that was previously unavoidable becomes redundant. That redundancy must be expelled. The universe does not store surplus energy without a configuration to hold it. This is the core reason energy is released. It is essential to emphasize that nothing about this process violates conservation laws. There is no mysterious surplus. The energy released is precisely the difference between two allowed configurations, one that costs more energy to exist and one that costs less. This difference is what nuclear physics calls binding energy. Binding energy is not energy stored inside the nucleus like fuel in a container. It is the energy the system would require to be torn back apart into its original, more expensive configuration. The fact that energy must be supplied to undo the binding is the mirror image of the fact that energy was released when the binding occurred. In the configuration-based framework, binding energy is simply the numerical measure of how much cheaper the bound configuration is compared to the unbound one. Why then is this energy difference so large? The answer begins with the nature of the interaction that governs neutron-proton binding, the residual strong interaction. This interaction is not a gentle attraction increasing gradually with proximity. It is steep, short-ranged, and highly nonlinear. At distances comparable to the size of nucleons, on the order of a femtometer, the energy landscape changes abruptly. As a neutron and a proton approach each other within this range, the potential energy of the combined configuration drops rapidly. The descent is not shallow, it is sharp. A sharp descent in energy means a large difference between the initial and final states, which must be released. This steepness has been measured and mapped through decades of scattering experiments. Proton-neutron cross-sections, deuteron binding measurements, and nuclear resonance studies all point to the same conclusion. The energy profile of the strong interaction at short range is extraordinarily deep. A second reason the released energy is large lies in what is being reorganized. Nuclear binding is not a rearrangement of peripheral components. It is not like chemistry, where electrons shift between orbitals while nuclei remain intact. Here, the rearrangement reaches the core of the configuration. The neutron and proton do not merely sit next to each other. Their combined state alters the allowed modes of motion, the internal energy distribution, and the effective degrees of freedom of the system. In chemical reactions, the energy landscape is shaped by electromagnetic interactions among electrons, operating at relatively low energy scales. Rearranging them yields modest energy changes. In nuclear binding, the rearrangement involves the conditions under which nucleons themselves remain stable within a joint configuration. The energy scale is correspondingly larger, millions of times larger. This difference is not incidental, it reflects the depth of the reconfiguration. In chemistry, breaking or forming a bond changes how electrons occupy available states around nuclei, while the nuclei themselves are largely spectators. In nuclear binding, the nucleons are active participants. The configuration defining their collective existence is altered. Because this reconfiguration is deeper, the energetic consequences are far larger. A third contribution to the energy release comes from what happens after binding. Once the neutron-proton system forms a bound state, it becomes dynamically quieter. Fewer internal oscillations are allowed. Failure or decay pathways remain closed. The configuration settles into a stable minimum. In energetic terms, this means the system no longer requires continual internal motion to maintain itself. Energy that previously supported internal motions is no longer needed. That energy cannot remain idle, it must exit the system. This exit takes concrete, measurable forms. High-energy photons are emitted, the bound nucleus may recoil, and in some cases, kinetic energy is redistributed among nearby particles. Every joule can be tracked. Experiments confirm the exact correspondence between the energy difference and the energy emitted. An important clarification follows naturally. If nuclear binding releases energy, why does it not release unlimited energy? Why does the process stop? The answer lies in saturation. The residual strong interaction does not grow indefinitely as more nucleons are added. Each nucleon interacts strongly only with a limited number of neighbors. Beyond that, adding more nucleons does not significantly deepen the energy minimum. At the same time, another effect grows steadily stronger: electromagnetic repulsion between protons. As nuclei grow larger, this repulsion increases with each additional proton. At small sizes, the strong interaction dominates, and energy is released when nucleons bind. At larger sizes, the balance shifts. Eventually, the repulsion offsets the stabilizing effect. Adding another nucleon increases the energy of the configuration instead of lowering it. This balance explains why nuclei have finite sizes and why the binding energy per nucleon peaks at intermediate mass numbers. This peak, observed near iron, is not coincidental. It is the natural outcome of competing energetic constraints. This framework also explains why energy release is selective. Not every combination of nucleons produces energy. Only transitions that lead to a lower energy configuration proceed spontaneously. Others require energy input. Fusion, fission, and radioactive decay all obey this same logic. The direction of spontaneous change is dictated by energy economy, not by force preference. Historical developments in nuclear physics reinforce this picture. Early in the 20th century, the scale of nuclear energy release was puzzling. Classical intuitions failed. Only with the development of quantum mechanics and later quantum field theory did the underlying logic become clear. Precise mass measurements revealed that bound nuclei weigh less than the sum of their parts. This mass defect, measured in kilograms and converted via E equals mc2 E equals mc2 E equals mc2, exactly matched the energy released during binding. Later experiments refined this understanding. Nuclear spectroscopy mapped energy levels, and particle accelerators probed nucleon interactions. Each result tightened the connection between configuration stability and energy release. Astrophysical evidence confirms the same principles on a grand scale. In stellar cores, nuclear binding reactions convert higher energy configurations into lower energy ones. The released energy supports stars against gravitational collapse and powers their radiation for billions of years. Neutrino detectors, solar observatories, and stellar evolution models all rely on the same binding energy calculations. The agreement between theory and observation is not approximate. It is precise. Mass represents the energetic cost of existence. Charge represents the rules by which configurations interact consistently. Gravity represents the geometric response to energy. Nuclear binding represents the release of surplus cost when configurations reorganize more efficiently. Nothing here is decorative. Each concept follows from the same requirement. Stability must be paid for, and the universe prefers cheaper configurations whenever they are available. One subtle but crucial implication deserves attention. Because nuclear binding involves deep reconfiguration, it is rare. Barriers are high. Transitions occur only under specific conditions. When they do occur, the energy release is unmistakable. This rarity is not a limitation, it is a safeguard. Without it, matter would rearrange uncontrollably, structures would not persist, and the universe would be noisy, unstable, and chemically barren. Instead, binding energy is released in discrete, regulated steps, allowing complexity to emerge. Binding explains why energy is released when nuclei form, but it does not end the story. Nuclear configurations do not remain frozen. Some decay, some split, some reorganize into entirely new states. Each of these changes respects the same conservation rules, yet they proceed along very different routes. In some cases, energy is released. In others, energy must be supplied. The difference is not in the bookkeeping but in how configurations evolve when stability is no longer static. To understand that, the focus must shift away from formation and toward transformation. If particles truly have no internal structure, how can all of these phenomena still occur? At first glance, this question seems contradictory. Particles are described as having no internal structure, no measurable size, no inner machinery, and yet they carry mass, electric charge, spin, participate in nuclear reactions, curve spacetime, and release enormous energy when configurations change. If there is nothing inside the particle, where does all this behavior come from? The answer begins not by redefining what is inside the particle, but by removing the assumption that physical behavior must originate from an interior at all. Modern physics does not treat particles as tiny mechanical objects. It treats them as states of fields, constrained by symmetry, and embedded in spacetime. Everything we observe arises from how these states are described, how they transform, and how they interact through fields that fill all of space. Nothing essential is missing. Nothing is hidden behind an inaccessible internal layer. When physicists say an electron has no internal structure, they are making a precise experimental statement. Decades of scattering experiments, from early cathode ray studies to high-energy collisions in particle accelerators, have failed to reveal any substructure, no radius, no internal components, no deviation from point-like behavior down to distances smaller than 10⁻19 10 carat, -19, 10⁻19 meters. In quantum field theory, the electron is fully characterized by a set of properties: mass, charge, spin, and its transformation rules under spacetime and internal gauge symmetries. These properties define what the electron is. Saying that the electron has no internal structure means that no additional degree of freedom is required to predict its behavior. Everything observable about the electron is already contained in its state description. This leads to a crucial layer. Particles are not objects in the classical sense. They are stable states of fields. In classical mechanics, an object has an interior, a surface, and moving parts. In quantum field theory, A particle is a localized excitation of a field that satisfies certain stability conditions. The field exists everywhere. The particle is a particular way the field can exist without immediately dissolving. A state can carry energy without containing smaller moving parts. A state can have momentum without internal gears. A state can interact without an internal mechanism mediating the interaction. Consider a standing wave on a string. The wave has energy, momentum, and a well-defined frequency, yet no object travels along the string. Particles behave similarly, but in relativistic quantum fields rather than mechanical strings. In this framework, mass arises from the energy associated with maintaining the state. Charge arises from how the state transforms under gauge symmetries. Spin arises from how the state transforms under rotations in spacetime. None of these require interior structure. A crucial point often overlooked: behavior in physics is determined by transformation rules, not by hidden composition. Spin is not caused by something spinning inside the particle. It is a property of how the particle's state transforms under rotations. Electric charge is similar. It arises from how the particle transforms under a phase symmetry of the electromagnetic field. Change the phase, and the state changes in a predictable way. That rule of transformation is what we call charge. Even interactions are governed by transformation rules. When particles interact, the interaction does not occur inside either particle. It occurs in the shared field between them. The fields respond to the presence of states, and those responses alter the evolution of other states. Modern physics places interactions between particles rather than within them. A useful way to see this is by examining what actually happens during an interaction. When an electron attracts a proton, there is no mechanical hook or internal attraction device. The electromagnetic field adjusts to the presence of both charges, mediating the interaction entirely through its structure and dynamics. That adjustment changes the energy of the combined configuration. The particles move accordingly. When a proton and a neutron bind, there is no internal restructuring of gears. The nuclear field configuration changes, and the combined state has lower energy than the separated states. Energy is released. When a particle curves spacetime, it does not push on spacetime from the inside. The energy momentum associated with the state appears in the stress-energy tensor, and spacetime geometry responds. Other states follow the altered geometry. At no point is an internal structure required. This perspective also explains why particles can participate in reactions that seem to demand internal change. In beta decay or electron capture, the particle does not rearrange internal parts. The state changes identity because the allowed transformations under the governing symmetries permit it. For example, when an electron is absorbed by a proton to form a neutron, the process is governed by the weak interaction. A quark flavor changes, and a neutrino is emitted to conserve quantum numbers. The transformation is not mechanical. It is a permitted transition between states under the rules of the weak interaction. The fact that this process occurs without any internal mechanical structure is not a weakness of the theory, it is its strength. The rules themselves are sufficient. Another layer of this idea becomes clear when considering what would happen if particles did have internal mechanical structures. Each internal component would require its own governing rules, introducing new symmetries, conservation laws, and potential failure modes. Predictability would collapse unless the structure terminated at some level. Experimentally, no such termination has been observed. Each attempt to probe deeper reveals not internal machinery, but simpler, point-like behavior governed by symmetry. This simplicity is what allows the theory to close mathematically. It is what allows conservation laws to hold exactly. It is what allows predictions to be made and confirmed to astonishing precision. In this sense, the absence of internal structure is not a limitation. It is what makes physics coherent. This coherence becomes especially important when considering conservation laws. Energy, momentum, angular momentum, and charge are conserved because the underlying symmetries are exact. These symmetries would be violated if particles had hidden internal dynamics that could exchange quantities invisibly. The reliability of conservation laws across nuclear reactions, particle collisions, and astrophysical processes strongly supports the idea that there is no hidden internal bookkeeping inside particles. Everything that matters is already visible in how states transform. From an experimental standpoint, this framework has passed every test. Precision measurements of the electron's magnetic moment match theoretical predictions to more than 10 decimal places. Scattering experiments reveal no internal size. Particle lifetimes follow symmetry-based calculations. Astrophysical observations align with predictions derived from the same field-based descriptions. Organizations such as NASA and ESA rely on these principles when modeling stellar interiors, supernovae, and the early universe. The James Webb Space Telescope interprets spectra using atomic and nuclear models that assume particles have no internal structure. These assumptions are not optional. They are built into the success of the models. There is a deeper consequence worth noting. If particles were mechanical objects with internal parts, the universe would be vastly more complicated and likely unstable. Small perturbations could excite internal modes, drain energy unpredictably, and open decay channels everywhere. Instead, particles behave as indivisible units. Their stability is protected by symmetry. Their interactions are constrained. This restraint is what allows complex structures, atoms, molecules, stars, and planets, to exist for billions of years. The absence of internal structure is what makes complexity possible. By now, a pattern has emerged across the series. Mass arises from the energy cost of maintaining a state. Charge arises from transformation rules under gauge symmetries. Gravity arises from spacetime's response to energy. Nuclear reactions arise from transitions between allowed configurations. None of these require an internal machine. All of them require consistency. Particles behave the way they do because the rules governing states are strict, limited, and unforgiving. Only certain states are allowed. Only certain transformations preserve the symmetries. Everything else is forbidden. This is why the world looks stable rather than chaotic. What this part leaves behind is not a final answer, but a clearer boundary. When physics describes a particle as having no internal structure, it is not claiming that explanation has ended. It is pointing to where explanation actually resides, in the rules themselves, rather than in hidden components. To understand a particle's behavior, nothing needs to be opened or dissected. What matters are the symmetries it obeys, the fields it participates in, and the geometric constraints that limit how it can exist and interact. With that perspective in place, the pieces presented across the series begin to align. If particles are understood as states, if interactions arise through shared fields, and if stability is enforced by symmetry rather than by internal machinery, then one question remains: what determines which states are permitted to exist at all and which are excluded? That question does not turn inward, it turns outward, toward the structure of the laws themselves. Part 10. How can a model with no internal structure explain mass, charge, forces, and nuclear reactions? If matter truly had no internal machinery, no hidden components, no moving parts beneath observation, it would at first seem impossible for it to display such a rich range of behavior. Mass resists acceleration. Electric charge attracts and repels. Forces shape motion. Nuclear reactions release energies capable of lighting stars. In everyday thinking, such effects demand inner mechanisms. Something must be turning, pulling, or rearranging inside. And yet, every precise experiment conducted over the last century has pushed physics in the opposite direction. Again and again, nature has answered the same way: nothing is found inside. No sublayers emerge. What remains is not emptiness, but sufficiency. The behavior of matter is fully accounted for without opening particles at all. The reason this works is not because physics ignores the question of what matter is made of, but because it answers that question at a deeper level. Matter is not explained by listing components. It is explained by identifying which states are allowed to exist, how those states behave under symmetry, and how they interact through fields and spacetime. In this view, matter is governed by rules, rather than assembled from parts. When physics describes a particle as having no internal structure, this is not a confession of ignorance. It is a deliberate, descriptive choice. No additional microscopic assumptions are required to account for all observed behavior. The electron does not need cogs. The proton does not need gears. Every measurable property arises from how the particle state is defined and how that state participates in the surrounding fields. This choice is not philosophical, it is empirical. High-energy scattering experiments have probed electrons and quarks at ever smaller distance scales. If internal structure existed, it would reveal itself through deviations in scattering patterns, form factors, or unexpected resonances. None have appeared. The simplest description continues to match reality. In physics, stopping at the level that explains everything observable is not a limitation. It is precision. Within this framework, mass is the first property to be explained. Mass is often imagined as substance packed into a volume. Modern physics replaces that picture with a more exact one. Mass is the energy cost of maintaining a stable state. Any configuration that cannot rid itself of its energy without ceasing to exist carries mass. This applies equally to confined radiation, bound nuclear systems, and elementary particles. Whether energy is stored in a field configuration, trapped by boundary conditions, or locked into a stable quantum state, its persistence requires energy. Through relativity, that energy appears as mass. No inner material is required, only an unavoidable energetic commitment. This idea has been tested across domains. In nuclear physics, bound nuclei weigh less than their separated components. The missing mass precisely equals the binding energy released. In particle physics, mass values determine reaction thresholds with exact accuracy. In astrophysics, stellar evolution depends sensitively on nuclear mass differences. All of these phenomena follow from the same accounting rule. Mass measures the energy that cannot be removed without destroying the state. Electric charge is understood in a way that does not require imagining anything hidden inside the particle. It is a label of symmetry, indicating how a particle responds when the surrounding electromagnetic field changes. In quantum field theory, interactions between particles and fields follow strict transformation rules. When the phase of a field shifts, charged particles adjust their behavior accordingly. This response is what defines the property we call charge. The magnitude of the charge determines how strongly a particle interacts with other charged states, but it does not correspond to a physical component inside the particle itself. This perspective also explains why charge comes in discrete amounts. The quantization emerges because symmetry categories themselves are discrete. A particle's state fits into one category or another. There is no smooth intermediate. Electrons and protons carry different charges not because of hidden substructure, but because they belong to different symmetry classes. The predictive power of this framework is remarkable. It accounts for charge conservation, maintains gauge invariance, and ensures consistency through anomaly cancellation. None of these require internal mechanisms, just mathematical symmetries that have been confirmed by experiments to extraordinary precision. Forces operate in a similar fashion. They are not invisible threads pulling between particles, nor mechanical connections hidden inside. Instead, they emerge from how fields respond to the presence of states and how other states evolve in those fields. Electromagnetic interactions occur because charged particles alter the surrounding field, influencing other particles nearby. Nuclear forces arise when certain combinations of particles lead to energetically favorable arrangements. Gravity manifests as the bending of spacetime in response to energy and momentum. In every case, no internal machinery is needed. Interactions arise entirely from the relationships between states and the fields permeating space. This relational view allows physics to explain all observed effects without assuming hidden interiors. Its success is evident at every scale, from atomic transitions to planetary orbits. Nuclear reactions provide one of the most demanding tests for any theoretical model. They involve drastic changes in energy, particle identity, and stability. If any hidden components were necessary, experiments in nuclear physics would reveal them. Instead, These reactions align perfectly with a state-based description. When a neutron and a proton bind, the system shifts from a higher energy state to a lower one. The difference is emitted as radiation or kinetic energy. There is no assembly of parts. The system simply adopts a more energetically efficient configuration. When nuclear reactions reverse, energy must be supplied. When a nucleus decays, the transition follows the allowed pathways determined by conservation laws. Every process is dictated by the possible state transitions, not by rearranging hidden internal pieces. This explains why nuclear energy is orders of magnitude greater than chemical energy. Chemical reactions rearrange electrons, while nuclear reactions modify the stability of nucleons themselves. The more profound the reconfiguration, the larger the energy involved. A clear pattern emerges from this perspective. The model succeeds because it isolates what is essential and discards unnecessary assumptions. It does not describe matter in terms of ordinary stuff or internal machinery. It describes the rules for what matter can do. Which states are permitted? Which are stable? Which can interact or transform? Once these questions are answered, the rest follows naturally. This framework closes the theory, avoiding infinite regress or speculative additions. It produces precise, testable predictions, which is why modern physics relies on it. The absence of internal structure is not a weakness, it is a strength. If particles contained hidden interiors, new energy scales, decay pathways, and conservation laws would appear, undermining predictability. Instead, nature is remarkably economical. States are simple, rules are strict, outcomes are constrained, and complexity emerges from combinations governed by consistent laws. This economy is not accidental. It underpins successful theories from quantum electrodynamics to general relativity. Together, these ideas lead to a unified understanding. Mass exists because maintaining a stable state requires energy. Charge arises from symmetry labels that dictate interactions. Forces emerge from field-mediated relationships between states. Nuclear reactions occur because certain configurations are energetically favored. None of these require hidden inner workings. All of them depend on strict, lawful behavior. This is why the framework is so robust. Each principle reinforces the others. Remove anyone, and the consistency collapses. Maintain them, and the world behaves coherently. Finally, this approach is powerful because of its humility. It does not claim to reveal ultimate reality. It describes only what can be measured, predicted, and tested, and it does so successfully. Observatories and space agencies, including NASA, ESA, and the James Webb Space Telescope, rely on models grounded in this framework to interpret phenomena from stellar interiors to the early universe. Its success comes from alignment with reality, not intuition. One last point is crucial. If matter is defined by the states it can occupy, by the rules that stabilize those states, and by the interactions among them, then the explanation does not lie hidden inside an unreachable interior. It resides in the structure of the laws themselves. Physics can describe these laws with remarkable precision. For the purposes of this series, that is enough. Mass, charge, forces, and nuclear reactions all follow because the laws permit certain patterns to exist, persist, and interact consistently. Thus, the search need not probe endlessly inward. It stops here, where the rules themselves accomplish the work. Thank you for following this series. I deeply appreciate your attention, and I encourage you to share where you are listening from or which part resonated most. Your reflections help shape what comes next.